Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is resistors in parallel. Our objective is to take a look at parallel, or side-by-side configurations of resistors. Additionally, we'll discuss the influence of shorts and opens inside parallel circuits. This lecture operates under the presumption the viewer has more than a passing familiarity with a 4-band resistor color code. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. A circuit is a complete path or a closed loop. The loop could be a single circular, rectangular, triangular, or any other shape forming a complete loop, or composed of many different pathways that at least one of which connects the two terminals of a voltage source. A closed circuit requires a closed path for a current to flow. Circuits composed of multiple resistors can assume numerous different configurations, among them a parallel or side-by-side relationship of resistors. Parallel configurations of resistors are those identified as having more than one path for current. Here's an example of a parallel circuit consisting of resistor 1 having a value of 330 ohms between node A and B, and resistor 2 having a value of 560 ohms also between node A and B. Any source current emanating from the positive terminal of the source has a choice of traveling through resistor 1 or resistor 2. Given not one but two paths to choose from, this implies that the source effectively sees less resistance than if the circuit were composed of just a single resistor. There are two methods of solving for the total resistance seen by the source for a parallel combination of resistors. One being a special purpose formula for just two resistors in parallel, and the other being a formula for any number of resistors in parallel. Ideally, both formulas should yield the same result. The first formula for just two resistors in parallel states the total resistance of a parallel combination of two resistors is equal to the product of the two resistors divided by the sum of the two resistors. Note the parentheses, which clearly indicates that summation occurs before the final division. The second formula for any number of resistors in parallel states that 1 over the total resistance of the parallel combination of resistors is equal to the sum of 1 over the resistance of those resistors constituting the parallel relationship. This formula is more universal in that it can be applied for any number of resistors. However, it necessitates the user be aware that the summation of 1 over the resistance of those resistors constituting the parallel relationship does not equal total resistance, but rather 1 over the total resistance. This necessitates the user take the extra step of inverting the final answer, a task that sometimes escapes the attention of individuals under stress. Regardless of the method you choose, the results from both formulas should yield the same results and serve as a great way of checking your work. If the formulas yield different results, you are doing it wrong. Since this configuration has two resistors, let's try an application of the two resistor formula. R1 times R2 is 184,800. R1 plus R2 is 890. 184,800 over 890 yields a total resistance of roughly 207.6 ohms. This implies that the source would be none the wiser if the parallel combination of two resistors was swapped out and a single 207.6 ohm resistor took their place. This easier visualization can be used in circuit analysis to simplify the analysis procedure. You'll note the shorthand for resistors in parallel is double pipe, implying a parallel simplification has occurred. Let's use the other formula to check this result. 1 over 330 plus 1 over 560 is roughly 0.0048. To obtain the final answer, we need to invert this value. 1 over 0.0048 is roughly 207.6 ohms as previously. You note the total resistance of this parallel combination of two resistors is less than the smallest resistor constituting this relationship. It makes sense. Given the source has a choice of two paths rather than just one, it is entirely understandable that the source would see less resistance. In fact, this is a great way of checking your work. The total resistance of a parallel combination of resistors is always less than the smallest resistor constituting the parallel relationship. If your answers or observations suggest otherwise, you are doing it wrong. Let's modify this existing parallel relationship by including another resistor, R3, having a value of 470 ohms in parallel. How will the addition of this third path in parallel affect the total resistance seen by the source? Think about it. No numbers. Will resistance go up, go down, or remain the same now that there's another path for current? If you're tracking, you should realize that the total resistance of this parallel configuration of three resistors should be less than the previous configuration of only two resistors because yet another path for current exists. Let's see if our calculations match our expectations. There's two ways of going about the calculation of total resistance. Perhaps the easiest and most direct means is making use of the more universal parallel resistance formula. 1 over 330 plus 1 over 560 plus 1 over 470 is roughly 0.0069. To obtain the final resistance, we need to invert this value. 1 over roughly 0.0069 is roughly 144 ohms. As we anticipated, the total resistance of this parallel combination of 3 resistors is indeed less than the previous one, composed of only 2 resistors, and is indeed less than the smallest resistor constituting the parallel relationship. This implies the source would be none the wiser if the parallel combination of 3 resistors was swapped out and a single 144 ohm resistor took their place. This easier visualization can be used in circuit analysis to simplify the analysis procedure. There's yet another way of determining the total resistance of this parallel configuration of 3 resistors. Recall that the parallel combination of R1, the 330 ohm resistor, and R2, the 560 ohm resistor, yielded a total resistance of roughly 207.6 ohms. We can use this fact and visualize this circuit as a parallel combination of R1 and R2, a simplification I'm calling R single prime, in parallel with R3. This is a perfect setup for the 2 resistor formula. R single prime in parallel with R3 yields a total resistance of roughly 144 ohms as previously. Let's put your understanding of resistors in parallel to the test with this set of example problems. For each parallel circuit, determine the total resistance seen by the source. Express all answers using proper engineering format to the 10th place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. For our first circuit, the source sees a total resistance of roughly 94.7 ohms. The second circuit necessitates interpretation of the 4-band resistor color code. Blue, gray, brown is 6-8 followed by 1-0 or 680 ohms. Gray, red, brown is 8-2 followed by 1-0 or 820 ohms. And finally, yellow, orange, brown is 4-3 followed by 1-0 or 430 ohms. The source sees a total resistance of roughly 199.4 ohms. For our third circuit, the source sees a total resistance of roughly 156.4 ohms. Finally, for our fourth circuit, the source sees a total resistance of roughly 254.1 ohms. Again, note how the total resistance of the parallel combination is always less than the smallest resistor constituting the relationship. If your calculations or observations suggest otherwise, you are doing it wrong.